Not
Right.
just physical details like the topology that remain the same in general, I mean, but also the characteristics of each of the qubits. Yeah, my name is Javier Cacheiro. I work at the Supercomputing Center of Galicia. And in this case, what we are going to talk about is a new type of resource that is a quantum computer. So we will look into what this means and how it's different from the typical computing resources that you usually are used to.
Yeah, personally, I have no idea what it means. I was very curious to understand. What is your kind of a setup for your quantum computer, and how it's your experience on managing and giving access also eventually to that?
Yeah, so there are different types of quantum computers. So this is probably some sort of confusion usually, that you think there is only one, but the quantum computers are still in this phase that we are still seeing different technologies that try to create quantum computers. So in this case, what we have is the most common one right now, that is a superconducting quantum computer. In the current state, that means actually, I mean, you can have the QPU that is like the CPU in standard computers, but it's a quantum QPU. So instead of calling it CPU, you call it QPU.
Yeah.
That in principle is very similar to a normal CPU from the point of view of the physical chip itself. But then the problem is that in a superconducting QPU, you need it to be at around 15 millikelvin. So that's
zero, absolute zero.
Yeah, almost zero to work, because it has to be in the superconducting state. So that means that in a normal computer, you would have a standard refrigerator with a fan. In this case, you need a very complex piece of technology. It's a dilution refrigerator that actually is the one that takes care of having this 15 millikelvin temperature. So
Cool.
This is the usual thing that you see when you look at pictures of quantum computers. Usually what you see is this dilution refrigerator, that this very nice piece that you see there.
So yeah, just out of curiosity, you mentioned CPU. I don't know why, but I used to imagine that more like an accelerator. Which one of the, so like a GPU where you can offload some kind of task? Is that correct? Is more on the accelerator part than a generic CPU?
Exactly. Right now, I mean, the main purpose of a QPU would be seen as an accelerator, similar to a GPU. Because even if a QPU can solve the same problems as a normal CPU, it's only efficient for some of them. I mean, so it would make no sense to run there a sum, for example, because it will be slower than a normal CPU. But there are certain problems where it can go much faster than a normal CPU. And those are the types of problems that you would want to offload to a QPU. For that reason, one of the main challenges right now is how you are able to integrate a classical computer, a HPC computer that can have GPUs, CPUs, with a quantum computer that would be able to do certain tasks much better, but others will be done in the classical part.
All right. So yeah, now thanks. It's clear to me at least. And how big and how, let's say, physically speaking, how it's made a superconducting QPU, and at your place in CESGA, how it's set up. So
exactly. This is another point that is usually confusing. If you measure normal CPUs, usually we are used to measure them by the frequency they have. So higher frequency, better. Now the number of cores, more cores, better. In the case of the QPUs, what you usually look at is the number of qubits.
All right.
So it's like a measure of how powerful is that QPU. The number of qubits that it has, that represents a set of the number of states that is able to accommodate inside. So in this case, what we have is a 32 qubit QPU, and you can see different QPUs that are trying to reach higher number of qubits.
All right.
But the other factor that determines how good a QPU is how good are these qubits. So you can have a lot of qubits, but if they are subjected to noise and to other effects, then you are not able to use them.
Use it. Yeah.
Exactly. So now the technological race is between these 2 points: how much qubits you can add, but how reliable they are. So at some point there were QPUs that had more qubits, and then they started to do QPUs with less qubits but more reliable.
All right. Okay. Nice. All right. So I think with this kind of introduction, we can understand. And how a user that develop this kind of stuff is able to offload specific tasks, specific circuits, right? So to this kind of center in this case.
Exactly. That's something that perhaps is also good to explain.
Yeah.
I mean, in normal computers, in the classical ones, we have high-level languages.
Yeah.
To program there that have been evolving. I mean, during the time, and now we have these high-level languages that allow us to do a lot of different things in an easy way. But in the case of quantum computers, we are not still there. So we have some high-level languages that basically allow us to simplify the creation of circuits. Because when you are talking about working with a quantum computer, basically you are talking to, you send a circuit.
All right.
And that circuit, instead of normal gates, has quantum gates. And then you measure the result of this circuit.
Yeah, the thing that resonates with me is experiencing with programming FPGA. So you are programming your firmware, and then you synthesize that in some way that the machine. So it's something
like that. Yes. In a sense, a quantum computer is like a programmable circuit that you can decide which gates you are going to use and how you arrange them. The higher level language that you have right now, that in general most people use Qiskit, allows you to create these circuits in an easier way. But you are still thinking about this way of programming that is quite low compared to classical computers.
Cool. And yeah, our users can work with the system, and in particular with your system and how you expose. Because in interTwin, we are working with use cases with people that actually doing science with something. And then we also there, and we talked briefly before at lunch actually, is that we need to understand the use case from the user and then give them access in some way that you can work with, right?
Exactly.
So our user usually work with this kind of stuff at your center.
There are two types of users, no? Let's say let's say more high-level users that they use one of these frameworks like Qiskit, and they program there. This is basically a Python program that generally mixes classical parts with quantum parts. That are right now the type of algorithms that are possible to run in the real quantum computers that we have right now. So for those type of users, what we do is that underlying this code, we provide a backend that is actually doing the translation. I mean, it's actually submitting the circuits and getting the results back. Okay. And then we have the other type of users that want complete control. In that case, what they can do is that can send directly the circuits. So you send the circuits and you get the measurements as a result. So you have both options, but the most common one is just to work at this higher level that you just programming Qiskit, and actually is similar to do it with a real quantum computer or with an emulator.
And out of curiosity, how they collaborate? So they are sharing code to build their circuits, or there is a format for these circuits they can store and share with other?
If you program at the high level with Qiskit, I mean, you don't actually work at the low level of the circuits. I mean, you create them, but you don't work at that level. But there is a standard format that is Quasam.
All right.
That will be like assembly in classical computers. So you have quasum that is the way that you express the circuits. But usually you don't work at that level. You work at a higher level that produces the circuits.
Okay, that makes sense. And this is, I suppose, at which level becomes dependent on the hardware you're running on?
Yes, the quasum that we quantum assembly language is one of the main ones. There is also Kir that does the same thing, but basically at that point, what you have is that you have these quantum gates, and there's different qubits that you are going to run. But the point is that the quantum computer does not have all the gates. Actually, it just have a very reduced set of gates. So there is another piece of software that is a transpiler. That is the one that converts from those gates to the ones that the current computer has. And then you also have to take into account the topology of the QPU, because
so there are additional steps under
under the hood that are done, because not all the qubits are connected with all of them. So you have to take also that into account, and that is done below. I mean, this is part that is done automatically. Well, it's a software that does that. It takes into account that. If you want to go to the lower level, then you usually work at the quasum level, and you do that part before. But you need that, because the QPU, in a sense, has just like a reduced number of instructions that is able to run. That's these quantum gates. And you don't want to work just with these ones. You want to work with the general ones, and then they are transformed to the right ones. The same with the topology. I mean, and it's rearranged so it can run there.
I can kind of imagine the complexity of the
usually you can see that. I mean, you can see the original circuit, if in case you are submitting how it was before with the gates that you had, and the one that actually ran in there that has much more gates there. Yes.
Very, very cool. And so, and regarding instead, I suppose you have one of these objects, right? That is how big it is, 32
qubits.
32 qubits, and it will be potentially served to multiple users, but not at the same time, right?
Exactly. It's like in the old times when you have the classical computers, and they were sequential because just one program at a time, so one person at a time. In this case, it's the same. I mean, the QPU can only run one user circuit at a time.
And sorry to interrupt you. How much time it takes to reconfigure a machine to?
This is also another interesting fact about the quantum computers. The longer a circuit can run is 100 microseconds. If you go above that, there is a time that is like the coherence time.
All right.
So if the circuit would last longer, then I mean, you know by sure that the result will be wrong, because you are not able to maintain the states that you were supposed to have there. So at most, one circuit can last 100 microseconds. It can last less. It depends on how many gates you place there. But at most 100 microseconds. And usually what you do is, instead of running just one, since in this case, you know, this probabilistic part, you want to measure. So you run several, they call it shots. So usually you run 100 shots. So that means that you can end running something like 100 milliseconds, one task, and then you will run a new one.
Okay, between the time I get access and I being able to see my results, so how long it takes usually? So I log in, I suppose, well, I know, I be honest. I know you give me access through some batch system, so you have people asking for access to, and they are waiting, and then when they are able to talk with either by the gateway or by full control, to pass their secret from the declarative way to being able to run things. So how much which is the step that takes most time? So I suppose you have a part where you are synthesizing your quasm, right?
Yes.
That will take
Can take long time.
Okay,
Can take long time.
can be.
But you can do it before. So the thing is that
Right.
if
So you
exactly. Usually, if it's a small program, I mean, you can run it directly.
Yeah.
But if you have a large one, what you would usually do is to do the compilation of the circuit. I mean, this transpilation beforehand. So then that's ready, and you are able to submit. So in that sense, it would be like a normal job where you first compile your program.
All right.
And in this case, what you get with that is that since the time that it takes to run in the QPU is very short, I mean, you will be much more efficient because you are not waiting to get the compiled circuit each time. So that's the usual way if you have a large circuit, because the compilation can take a long time if it's a complex circuit.
All right. I see. So you have a first part where you do not need the physical hardware to be ready, where you synthesize your code, and then and the second step, how long it takes. So once I have my cusp to load it into the machine and submit.
Yeah, there is one important part there that is to generate this code. I mean, the compile code, this transpile code.
Yeah.
You need to know about the details of the QPU, not just physical details like the topology that remain the same in general, I mean, but also the characteristics of each of the qubits. Because when you are going to create that version of the circuit, you would want to run in the best qubits.
All right.
So there are certain parameters that are
so there is kind of a bidirectional communication. So
no, you have like in this case are the results of the calibration process. That is something that probably most people are not aware. These systems require to be calibrated each day. So each day there is a window of time where you look how the system is performing.
You are mapping
exactly, and you fix or you tune things that could be going wrong. With those data, the data of the calibration is with the ones that you do the transpilation. I mean, this optimization process that is part of the transpilation, because the gates are the same, but it could be the qubits that before had better times, now they have not so good times, and you want to move to another.
I see.
Yeah.
Yeah, very nice. So, okay, last two questions. The first one I had in mind is, we mentioned Slurm as a way to access it, to manage the requests from many users. We in the interTwin project, we were actually planning before this this chat to integrate this into the interlink machinery, so you can in principle submit something from outside, land into the Slurm queue, do all the steps that you mentioned, and access to this machine. You will know more about this once done. But regarding this, so what are some category of use cases that you are actually serving? Not the use cases really in detail, but just to give an idea to people what kind of problems can be targeted with this kind of machine. So if you have category, I know from interTwin, for instance, there is the lattice QCD activity, but if you have anything else that can be of interest, yes, please.
Yes, well, I'm not an expert in the applications area, so there are different use cases. Some of them, I mean, are mostly related with optimization problems, because this type of hybrid problems, where you use a classical part and just run some quantum circuits to guide the optimization. I mean, so they work together, the classical and the quantum part, are the ones that now are more feasible, because the current quantum computers are still very noisy.
All right.
And in that case, I mean,
they have to be resilient to noise in some way.
Exactly. If you want to do something like the Shor algorithm, the one that we all know, to break the internet because it will break the encryption. Okay, for that one, I mean, you need a quite reliable system, because you will get the result. But for optimization, I mean, you are just moving in a curve trying to find the minima. So it's more resilient to errors. So for those type of problems, there are many different applications. One of the perhaps most striking ones is one that we were doing, that is to find a flavor for beer, and they were using that to try to find a solution to the problem of what could be an improved version. So there are very, let's say, unexpected applications. Yes.
Yeah, I see. So, okay. One curiosity, how physically big are these machines? So they will fit in a room like this, or in a...
Yes, they are. Well, for everyone to have an idea, the QPU would be like a normal CPU, but that will go to the bottom of a large structure that is like a bin.
Yeah, something like
yes, that inside that is this dilution refrigerator. That it has different plates that make that the temperature goes down till 15 millikelvin. So that's big. I mean, it could be this more than the size of a person. And it has a frame around it that, I mean, takes care of the vibrations to avoid them. So you have that one, and then you would have a normal rack of classical computers that take care of controlling that one, because there you have the QPU, but then you need the equipment that is able to produce the signals. These are microwave signals that go to the QPU. So
you have electronics.
You have the electronics in this rack, and then you have another rack that is the one controlling the dilution refrigerator. So in general, you will have this frame with this structure that is a typical that you see, that inside has the picture that we all see. That when you see a quantum computer, you just see the refrigerator. You don't see the QPU, but that's the one that is inside, and these two racks. So it's in a standard data center, it could be the size of, I don't know, 5 racks.
Okay.
So it's
not that big.
Not that big.
Okay.
Not that big. It's very special in the sense that it's very different from the rest of the machinery. You need to have there also the nitrogen, so to refill it, but it doesn't need a lot of space. It's also true that it's also something to take into account. It's just one QPU. So for one QPU, it's a lot of space. If you would want the same number of CPUs that we have in a system, that would be impossible.
A region.
That could be totally impossible. But from the point of view of usually you just have one of these quantum systems, I mean, the space is not so big.
All right. So yeah, nothing more to ask, I suppose. Thank you for joining.
It's a pleasure.
It was very, very, very interesting. So thank you again. Let's keep in touch and see how the integration with Intel goes.
That's it. It works fine, and people can enjoy the system.
Okay,
thank you very much.
Thank you. Bye-bye.